Good evening. It is Thursday, February 13th, 2025, and welcome to the 2025 Kamloops Exploration Group Lecture Series. My name is Sean Toom, and over the next couple months, KEG is extremely excited to host presentations from fantastic experts. Before we get started, I would like to first acknowledge that we are speaking today from Kamloops within the territory of the Kamloops Teshishwapnik peoples, on whose land we have the privilege to work and play. This year's series will be hosted through a hybrid style with some online and some in-person events. Today obviously is online. The next one will be in person. As a non-for-profit organization, the Kamloops Exploration Group relies on sponsors to aid in hosting events such as the lecture series. And tonight, we would like to thank very much ALS Geochemistry for being the sponsor for the 2025 lecture series. I'd like to inform everyone that your microphones are muted and the video cameras are turned off. If you have any questions throughout the talk, please write it into the Q&A tab. And when we get to the end of the conversation, end of the portion of the conversation, we'll reach those question and answers at that time. Tonight, we're excited to welcome Yannick Le Moigne. And if you would like to know more about Yannick, his biography can be found on the KEG website. Yannick is coming tonight from Vancouver, where he's also received his PhD from Simon Fraser University in 2020. He's a research scientist with the Geological Survey of Canada and will be speaking today on the chronology and dynamics of Canada's deadliest volcano eruption, which occurred in BC within the Nass Valley, northwest of Terrace. I've been fortunate enough to fly over with a helicopter over the area, and it's a beautiful area and extreme wilderness, very remote. And Yannick's been over, he told me every portion of this beautiful landscape. So without further ado, Yannick, the stage is yours.
Okay, can you see my screen? Thank you very much for the introduction. I'm very happy to give this talk tonight. And I will do my best to summarize what I did during the 4 years of my PhD. And it will be about the chronology and the eruption dynamics of Canada's deadliest volcanic eruption, which occur at Tseax volcano. The picture of Tseax is in the background of the first slide over here, about 300 years ago. And before I start, I would like to acknowledge a lot of institutions listed on the slide over here, and also the Nisga'a First Nation. It's thanks to them that we are able to give this talk and to produce all the research that has been done at Tseax over the past few years. And if you want to know more details about what I'm going to talk about, there is a list of several papers that have been published recently. Before going directly into what is Tseax and where it is and how it erupted 300 years ago, I would like to introduce you to the two types of volcano that exist on Earth. We have to the right-hand side over here in blue what we call the polygenetic volcanoes, and on the left side we have what we call monogenetic volcanoes. First of all, the polygenetic volcanoes are the ones you are probably the most familiar with. They are big, they are huge, they are very voluminous, and they tend to erupt very explosively. Example of those, you have Mount St. Helens or Mount Baker in the US, and also Mount Garibaldi in British Columbia, just near Squamish. But those are not the topic of today. The topic of today are what we call the monogenetic volcanoes. Those are small in volume, and they erupt only once. So they have a very short-lived volcanic activity, and they are very small in volume compared to the volcanoes I showed previously. And Tseax is one of them. And actually, Tseax is part of one of the end member of those monogenetic volcanoes. Very small in volume, erupt only once, and it's a very specific type of volcanoes. So where is Tseax now? Well, as you may see, British Columbia and Yukon, they are part of the Pacific Ring of Fire. It's a chain of volcanoes that goes from Chile up to North America and then Alaska down to Japan and New Zealand on the other side of the Pacific Oceans. And those volcanoes are the result of the movement of the Pacific oceanic crust underneath North America, and it produced a chain of volcanoes in US and in Canada. And in BC, we have several volcanoes, including Tseax volcano, that are more or less directly related to the solution of the Pacific crust underneath the North American crust. The map on the left over here, it shows the location of all the volcanoes in Canada, all the recent volcanoes in Canada. Each red dot is a volcano, and each blob, yellow blobs and orange blob, correspond to a volcanic province. So just north of Vancouver, you have Mount Garibaldi, Mount Meager, that maybe you have heard of, and it belongs to the Garibaldi volcanic belt. But as you go north, there is another volcanic belt that is called NCVP. NCVP goes for the Northern Cordillera volcanic province, and it's the largest volcanic province in Canada. It comprises more than 100 quaternary volcanoes, so very young volcanoes. And it's also the most active volcanic zone in Canada, with on average one eruption every 300 years, more or less. So Tseax is the red star over here, and it's at the south of the NCVP. And it's the second youngest volcanic eruption in Canada. The youngest one is noted by the letter LF here for Lava Fork. And Lava Fork is only 200 years old, let's say. But Tseax is about 300 years old, and it's the second youngest volcanic eruption. So not only being the second youngest volcanic eruption, it's also the deadliest volcanic eruption, because during the eruption, we have an estimation of 200 Nisga'a people that died during the eruption. So the graph that is shown over here, each bar represents a volcano in the US, and the colored bar correspond to volcanoes in Canada. And they are ranked over here according to the overall threat score. So in red are the volcanoes that are very dangerous, and in green are the volcanoes that are less dangerous. So on the left over here, you have Mount Garibaldi, which is actually the most threatening volcano in Canada. And in green, you have Tseax volcano over here that is having a low threat score. Nevertheless, despite a low threat score, it is still the site of the deadliest volcanic eruption in Canada. So it's still very important to study these volcanoes despite having a low threat score. So the threat score is basically calculated from the volcanic history of the volcano and the number of people living near the volcano. So we go back to the map here on the left that I showed you previously. And now if I do another map that is a zoom very close by to Tseax volcano on the right-hand side, you can see the outline of the lava flow associated with Tseax volcano. So it erupted in a mountainous area, and the lava flow flowed down the valleys until it reached the Nass Valley over here and near the two Nisga'a villages. Tseax is not alone in the area. In yellow are all the other recent volcanic outcrops mapped in near Tseax volcano. We don't know much about the other volcanic sites over here because they are very, very remote, and it's very difficult to access these areas. We are very fortunate that we can access Tseax volcano quite easily because there is a road that goes from Terrace about an hour drive south to Tseax volcano over here. So there is a very rich oral story from the Nisga'a First Nation about the eruption of Tseax. However, I'm not allowed to tell the story myself because it's for them to tell the story. And even if I do, I will not make justice to the story. But using some of the information and some of the oral stories, we are able to reconstruct the story of the volcano. And the map I show here is what was the geography before the eruption. So in blues are the rivers. You have on the upper left, you have the Nass River, which is one of the most important river in BC, and it was flowing here in the Nass Valley towards the left-hand side. Along the Nass River over here, there were the locations of 3 former Nisga'a villages along the shores of the Nass River. A bit further upstream, some smokehouses, and a bit further upstream again, a fish camp near a small lake. And as you go upstream again and again and again, you go up Crater Creek Valley, and this is where the Tseax volcano will be located. So it's believed that in these 3 villages, about 2,000 people at least were living there. After that, the eruption occurred, and this is how the landscape is looking now. So in green and orange and yellows are the lava flows we have mapped, and the volcano is shown in red over here. So in green, you have long lava flows. The dark green and the light greens are what we call Payoyoi lava flow. I'm going to show pictures of this in the next few slides. The dark green one is actually 32 kilometers long, and the light green one is 21 kilometers long. So these are very long lava flows. Closer to the vents, closer to the volcano, you have 2 other lava flows that are thicker and more viscous, what we called RR lava flows. So Payoyoi and RR are 2 terms that we use for describing lava flows, and they are terms we use also to describe lava flow in Hawaii. So overall, the total volume of lava flows that was erupted during the eruptions was about 0.5 cubic kilometers. So the next few slides, I'm going to show you some field pictures of what the lava flow and the lava looks like on the field. So I'm going to start by showing you a picture of RR lava flows. This picture I show where you have flow 4 and flow 3, so the 2 latest flow that overlap each other's. And you can see the colors first is very orangey and yellowish. It's because most of the flow and the lava over there, they are covered by recent mosses and lichens. That's why the entire flow is looking this color of beige to orange and covered by moss. But overall, you can see the RR lava flows is very rough with loose angular fragments up to 2 meters in diameters. Then as we move, then the lava flow in this location flowed into a lake. And one of my colleagues, Steve Kwan over here from Quest University, had a sonar mounted on one paddle board. And he managed to do paddle boarding all along this lake over here in order to know how far the lava extended into the lake. We wanted to know how far the lava is extending into the lake because we wanted to have an idea of how much volume went into the lake. And so the map on the right is showing the bathymetry map of the lake. So basically the topography of the lake bottom. And there is a steep slope over here somewhere located over here. And we believe that this steep slope over here at the lake bottom represents the age of the lava flow field. So it didn't went far away into the lake, just a couple of 100 meters at maximum. Now, as we move toward the Nass Valley, where most of the lava volume is, and where the Nisga'a villages were located, we enter into a wide open flat valley. And as you can see, there is not too much tree covers on it because everything is the recent lava flow. So the panoramic view over here is as we were standing on top of the canyon city over here, which is one of the Nizhga village. And you can see a nice panoramic view of the lava plain over here. So the field of view, to give you an idea of the size, the field of view here is about 15 kilometers wide. And the entire lava plain here is covered by a lava flow of 10 to 15 meters thick. So it's very voluminous. And it is bordered by the Nass River on this northern margin over here. So the lava plain here is about 12 to 15 kilometers long and up to 3 kilometers wide. And because it's you don't have any forest in the area on the lava plain and it's easy to access, we were able to map in very detailed precision the lava flow morphologies in this area. So this is just a sketch of the lava flow morphologies. And each symbol here, SL, LR, etc., refer to a specific lava flow morphologies. So we have Yumoki to lava rise, slabby, and pressure ridges. I'm going to show you a picture of these 5 different lava flow morphologies. And I would like to imagine you to travel from the lava flow front as we hike up towards the lava flow interior. The lava flow morphologies will change gradually from Yumoki towards slabby and pressure ridges in the middle of the lava flow field. So we start from the flow front, and we have Yumoki Payayoi. You have a map view of the Yumoki Payayoi on the left, you have a field photo on the right, and you have a cross-section of a Yumoki Payayoi on the lower left. So these are made of very irregular rough surfaces with hummocks that we call the tumulus, with in the middle a crack that we call inflation cleft. And in plain view, you can see they form like intercrossing figures. It's when the lava flow was slowly advancing into the lava plain. It's not a huge mass advancing like this. It was fingers intercrossing themselves and coalescing eventually. And as you move upstream, they coalesce more and more, and behind the lava flow is inflated, and the surface becomes less and less rough. And you can still see hummocks with the central inflation cleft, but this surface is progressively disappearing and transforming into very, very flat surfaces over a wide area that we call lava rise payayoi. These are fully inflated payayoi, is the final stage of a truly inflated payayoi. Super wide, you can walk on this for hours and hours without falling into a crack or whatever. They are super smooth surfaces. Sometimes you have a deep pit probably due to a collapsed lava tube underneath. And as you move upstream a bit more, the surface becomes rougher again, but this time it's because the internal pressure of the lava flow was high enough to disrupt the upper crust. So the upper crust is broken into pieces, what we call slabs, and those slabs are up to 2 meters wide and 30 to 50 centimeters thick. And the more you disrupt, the more those slabs are smaller and smaller. So these were the major volcanic features you can see on the Nass Valley lava flow. But there is a long portion of the lava flow here along the very narrow Tseax River Valley. And unfortunately, I cannot show you picture over here because it's fully covered by forest now, and also by numerous streams and ponds and lava lake, as you can see on the aerial picture on the right side over here. But we know that there is the lava flow in this area as well. So let's go to the volcano over here. Let's have a look at what looks like the volcano that produced all of these voluminous lava flows. So this is an oblique view of the volcano. So north is going on the upper left. And the Tseax volcano is quite small, actually, especially if you compare to the volume of lava flow that it erupted. The volcano is about 400 meters wide, almost perfectly circular. It's a tephra cone with an inner central crater here. And it is surrounded by a U-shaped spatter rampart. I'm going to show you what it looks like. It's a U-shape with, in the middle, the tephra cone. To the north, across Melita Lake, you have another small satellite cone, another small tephra cone. And from these, all of these, you had the lava flows going down the valley toward the lower left of the screen. So the inner crater, the central crater is looking like this. It's about 80 meters wide, very steep at the bottom. And all of the area around the volcano is covered by a fragment of lava, what we call ash and scoria. They were deposited during the explosive phase of the eruption. And then sometimes it's more than 2 meters deep close to the volcano, and it's thinner and thinner as we go away to the volcano. On the map over here, each yellow point is where we measure the thickness of those ash and scoria deposits. And it was very fun to dig into the forest in order to get an idea of how much material, how much explosive activity occurred at the volcano. So the spatter rampart is forming a U shape around the tephra cone, and it's basically an accumulation of volcanic bomb near the vent, very close to the lava fountain. You have accumulation of material that were falling from the lava fountain and progressively forming a wall of spatter, a wall of fragmented material like this. And it formed a U shape like this. Instead of a circular feature, it formed a U shape because you have to allow all the lava to flow down this side of the volcano. So the spatter rampart was only stable on this part of the volcano because all the lava flow was flowing down that direction toward the lower left of the picture. On the other side, the satellite cone is very small, only 20 meters high, but was a site of early activity during the eruption. And this is a map view of the volcano, as I said. In orange is the lava flow filling the bottom of the valley. And in red are the inner tephra cone and the U-shaped spatter rampart from which escaped most of the lava flow towards the valley on the lower left. So we sample a lot of materials and we crush and we the samples in order to analyze them under the microscope and other instruments to get an idea what were the physical conditions that give birth to the eruption of the volcano. So we took samples, we analyzed under the microscope, and we have a close view on the upper right of the microscopic details of the lava flow. So you can see in bright colors, white and pink and green, etc. Those are the crystals, olivine and plagioclase that form the magma of the volcano. So we analyzed those crystals in order to get an idea of what were the mechanisms during the eruption. So there are differences in the petrology. So the crystals in the Tseax magma. When we took samples from the main lava flows, they are crystal poor. As you can see, you have only a small amount of larger crystals. When we took samples of the second lava flow, there are crystals a bit more than during the first flow. But as we took samples toward the later stages of the eruption, the last lava to be erupted, you have a lot of crystals, especially a lot of plagioclase, those white to gray tabular crystals. The other crystals we see, they are olivines, very bright colored, like in pink, green, or yellow. And the black ones are oxides, iron and titanium oxides. I would like to point you that there is no clinopyroxene, which is a very common mineral in Volcano, typical of Tseax. But in this case, we do not have any clinopyroxene seen under any samples we collected. Clinopyroxene is not existing at Tseax, and this is very important for the next few slides. Another important observation is that these three mineral phases, olivine, plagioclase, and iron titanium oxides, they usually exist together as mineral clots that we call glomerocrysts. They are a blend of mineral agglutinated together with olivine, plagioclase, and iron titanium oxides. So at one point during the evolution of the magma before the eruption, the conditions were set for those three minerals to crystallize together at the same time, but still without no clinopyroxene. So we wanted to know at what condition the magma were sitting under the surface before the eruption. And this can be explained in this graph. So this graph is showing you at the top, the scale over here is the temperature in degrees Celsius, going from 1000 degrees to the left to 1250 degrees on the right. So it's colder on the left, warmer on the right, very warm actually. And the y-axis over here, the vertical axis, is the depth below the surface. So the surface, it's here at the top, and it's going in depth in kilometer as you go down. And the line in the middles, they represent at what condition of temperature and depth those minerals would appear in the magma. So I'm going with you to the upper right. The magma is fully liquid, no crystal, fully liquid. And if you imagine the magma cooling toward the left, so the temperature is becoming colder and colder, you start crystallizing iron, titanium oxide, and then olivine, and then CPX, and then plagioclase, etc. So once you cross those lines, now the magma is not fully liquid. It is a liquid plus those crystals. But we know that we do not have any CPX. So we know we are not on the lower part of the graphs. So the magma was not sitting here. Otherwise, you would have CPX in large amounts in those samples erupted at the surface. If the magma was sitting here, it was fully liquid, and then it was crystallizing some crystals, which are iron and titanium oxide, olivine, and later plagioclase. This is what we have in our sample. So thanks to this graph, we are able to say that the magma was sitting at depth no lower than 17 kilometers beneath the surface. So this is another example. So we know the depth. Now we want to know the temperature at which the volcano erupted. So again, we have the temperature over here on the lower axis. It goes from 1150 degrees and it goes down to the right until 950 degrees Celsius. And the volume of the crystals here represent the amount of crystals that were crystallizing as the magma was cooling. We know that we have those glomerocrysts of olivine, plagioclase, and iron titanium oxide. So we need to find the condition at which those three crystals were forming together. And there is only one way to find out. It's by cooling the magma at temperature of these degrees, 1080 degrees to 1096 degrees. This is the eruption temperature at Tseax. It's quite cold compared to eruption temperature during Hawaiian eruptions. But obviously, to give you an idea, it's more than 4 times higher than the maximum temperature of your kitchen oven. All right. Now I'm going to show you sketches and videos of what happened at the surface. What was the eruption if someone was standing near the Nisgaard villages, or if someone was standing near the vent, the volcano, what it would have looked like. So we have divided the eruption into 2 periods, what we call period A and period B. Period A was the eruption of the first flow, flow 1, as well as the second flow, flow 2. And then following maybe a pause, a very brief pause during the eruption, we have the period B, which was occurring during the emplacement of flow 3 and flow 4, the 2 late flows. So on the left-hand side, you're going to have the map view of what happened during eruption. And the right-hand side is showing you a 3D sketch of the volcano as it evolved through time, right? So it started like this. During period A, you have the eruption of lava flow 1 in green over here, the long Payayoi lava flow that reached the Nisgaard villages and also the Nice River in the Nice Valley. So we did some numerical calculations, and according to field observations, this lava flow was in place in no more than 100 days, perhaps just a few weeks. And on the map, you can see in dashed white line the time in hours for the lava flow to reach a certain point. So the lava flow was coming out from the volcano. It reaches the bottom of Crater Creek Valley here only after 6 hours. The location of those fish camps over here, 17 hours after the beginning of the eruption. And the first villages was flooded by the lava flow only 32 to 41 hours after the eruption. So a day and a half, 2 days. And the third villages, 2 to 3 days after the eruption, these villages was also flooded by the lava. So very quick, very fast advancing lava flow. To give you an idea, this is almost 30 kilometers away from the vent. Now at the vent, what happened is you had opening of a crack in the ground, allowing for lava fountaining. The magma was reaching the surface at high speed, and so you have a lava fountain producing a buoyant plume of volcanic gases, and a lava fountain over here, from which you have the lava flow escaping. Because the lava flow 1 is the most important into the eruption dynamic and the most voluminous one, because it's the one that reached the Nisgaard villages and potentially caused the Nisgaard fatalities, we wanted to know more about this, and we wanted to produce a numerical modeling of the lava flow during the eruption. So we were able to do this numerically by inputting into our model the topography of the area, and we wanted to simulate the lava flow during the eruption. So the model over here will show you the lava flow advancing over time. You have the time over here in hours, and you will see in green in the next second, in the next few slides, the lava flow advancing in the video. So we choose a different lava viscosity in order to best replicate what we observe on the field. And the best candidate is to have very low lava viscosity. The viscosity basically is the ability, the resistance to flow. The lower the value, the more fluid the lava is. So a viscosity of 225 Pascal second is basically the viscosity of a peanut butter. So you have to imagine a lava flow as fluid as peanut butter, but at almost 1200 degrees, flowing in the valley over here. So the video is running, and you can see in green, this is the lava flow coming off from Tseax, and it's reaching the first villages and the smoke houses and the Nice River very quickly. half a day to reach the Nass River and the Nass Valley. And you can see here now it's reaching the first two villages after one day. And it's pushing the Nass River in blue towards the northern side of the valley. And it's also flooding the Nass Valley. And finally, after one day and a half, 2 days, the lava flow is finally reaching the last villages further downstream. And you can see that numerical modeling is almost perfectly replicating the final shape of the lava flow as we see it today. Now, if someone was standing over here, actually there were people standing over here because in these 3 villages, up to 2,000 people were living there. This is what they would have seen, a very flat area that is progressively covered by a slow advancing lava flow. This is a video taken in Hawaii recently in 2018. You can see the scenery would have looked like similar to this, a slow advancing lava flow, perhaps 1 meter per second maximum. So you might say, oh, I could get away from this rapidly. And you are true, because usually people are not dying from lava flows. So we might find a way to explain why the Nishga people died during the eruption, despite having a lava flow that was advancing slowly. One reason is the interaction between the lava and the Nass River, the interaction of a very, very warm 1200 degrees lava into a cold water, the Nass River. When we look back at the oral Nishga traditional stories, there are stories talking about a spirit cloud, fumes spreading ahead, and a poison smoke as well. It's usually the case when you have lava entering into a water body, you have a strong lava degassing, and you have therefore a lot of CO2, SO2, or other volcanic gases that are released into the atmosphere. And those deadly gases, and those gases could be deadly to the population nearby. This is often the case in Hawaii, for example, when you have lava flows entering into the ocean. As you can see on those pictures, you have a lot of volcanic gases, a lot of plumes, and a lot of smoke that could be released. And this smoke could include a lot of deadly volcanic gases. So this could have happened also at Tseax, where you have a very voluminous lava flow entering into a very strong river, the Nass River. So a lot of water was there already. And therefore, you could imagine a lot of volcanic gas in the area during the eruption. And if those gases are concentrated enough, they can kill you quite easily. So some of the fatalities might be explained by the poison smoke related into the Nishga stories. Now, the eruption continued. It was chaos into the Nass Valley, but the eruption continued at the vent. And after the flow number 1, there was a second flow that was erupted shortly after. And this one also reaches the smokehouses, but it did not enter into the Nass Valley. But this flow is also quite voluminous, and it was in place in 5 to 10 days. But at this time, near the vent, the eruption decreased in intensity, and the lava curtain also decreased in length and height and intensity. And it is at this time that you form the outer U-shaped spatter rampart. So it was a U-shaped, as I say, because you had to allow a gap for the lava flow to escape the volcano. So if someone was standing on top of the ridge over here and looking down the volcano during this phase of the eruption, you would have seen something like this. a high and powerful lava fountain ejecting into the air volcanic bombs and spatter and ash and scoria falling around the volcano, and it formed a mound of volcanic material, forming the outer U-shape spatter rampart. Again, this is pictures from Hawaii, because we believe that the eruption of Tseax volcano was very similar to a typical eruption in Hawaii. After that, maybe after a very brief pause, the eruption continued. And this time with the eruption of the two late RR flows that are more crystal rich. So the magma and the lava was more viscous. And so it has increased the intensity of the eruption, and it became a bit more explosive. And so the lava fragmented a bit more and produced perhaps a plume that was higher up in the atmosphere. And it formed also the inner tephra cone in gray over here. So this is what this is the end of my talk. I hope I managed to give you a good summary of the eruption dynamic at Tseax. It was an eruption that lasted maybe 1 to 4 months in total, about 300 years ago. It's a monogenetic volcano, so it's a one-off volcano. There is very little chance that this volcano erupt again in the future. However, it's located in a volcanic province where there is one eruption every 300 years, more or less. So potentially other similar eruption might occur in the future in this area in Northwest BC. We don't know. We managed to get a numerical modeling indicated that the lava flow reached the Nisga'a villages in less than 2 days. It displaced the Nass River, and probably the contact between the very warm lava flow and the cold Nass River produced a poison smoke, as they say in the Nisga'a story, so volcanic gases that might explain the Nisga'a fatality. Thank you very much.
Thank you very much, Yannick. That was a great presentation. Well thought out, great slides, very good figures. Really impressed. I think everyone on the call is really impressed too. It was really well done.
Thank you.
I've got a handful of questions for you. Just wondering if you've encountered any other oral histories with any of the other nations in the area. I know Niska is the one that we're talking about, but what about the other ones? Is there anyone else that you've talked about that there's whispers or anything around that area?
No, I always heard about the Nisga'a stories on the volcano. Other oral stories for this volcano, no, I don't know.
Okay. And you said that these volcanoes only erupt once, these monogenetic ones. Why is that? And why do they only erupt once where other ones, I know that the other ones are much bigger and maybe more volume of lava, fluid flow, but why are they only one time?
Well, the other ones, they erupt many times because you have a stable magma chamber, magma plugging system underneath, because you have a constant flux of magma coming from the mantle underneath the crust. And so the system is much more stable. In those cases, like Tseax, the monogenetic volcano, it's one-off because it's very unpredictable. Well, it can erupt just once, and yeah, that's all.
Sure. Yeah. You said the deadliest part of the volcano could have been the gases, also the flow, obviously.
Yeah.
But what about is there any evidence for outside of the volcano, around the center, around the cone? You said there's ash, but outside of the cone, is there, a couple kilometers away, is there any ash, or is there any evidence of pyroclastic flows that would have come at the direction down the Nisga'a Valley?
Yeah. So when I say ash, it's not ash as we understand it from pyroclastic flow. So those type of volcano at Tseax, they don't produce pyroclastic flow. it's only scoria. So it's just fragmented material that fall around the volcano. When I say around, it's just a couple of kilometers max. The villages were located more than 20 kilometers away. So the Nishka deaths probably were the result of the lava flow and the interaction with the Nass River, but not directly related to the explosive activity at the volcano itself.
Okay. And you mentioned that in the volcanic provinces, these volcanoes will erupt roughly one in every 300 years. Doing the simple math, it's about 300 years away.
Yeah.
So what would be the next area?
No, I mean, it's very rough. Those are numbers. You don't remember those numbers. Those are very rough because there are so many volcanoes and they are so remote that we don't even know how much they are. And we don't really know the date of those volcanoes. So yeah, very unlikely to have an eruption in the near future.
Okay, you put my mind at ease. Thank you.
Yeah.
Maybe not you though. You're in Vancouver next. One of the big ones, Mount Garibaldi, right? So maybe not Vancouver.
Yeah.
So next question: what would be the to a volcano like this, one of these monogenetic ones? What would be any kind of warning signs that that someone would have had a kilometer away, 20 kilometers away? Like, is there any kind of warning that they might have had?
A couple of warning signs. Yeah, you might felt. Oh, so those volcanoes erupt because you have a rising of the magma into the crust toward the surface, and as the magma is moving up, it's shaking the ground. So you might felt some earthquakes before the eruption, like weeks, months before the eruptions. This is something so currently we are producing here at the Geological Survey the first monitoring of Canadian volcanoes, looking at the volcanoes from space. And we are looking if they are deforming or not. Let's say a volcano is going to erupt in the next month, years, or decades. You will see deformation of the volcano from space. You will see the volcano inflating or deflating. And this is something we are monitoring right now. We are currently building the system, but eventually we will do that. So as the magma is moving underneath the volcano, at the surface, you will see the volcano inflating or deflating. And this is something we can use as precursor sign of potential future volcanic eruptions also.
So with that movement, the vertical movement, I'm sure that's probably happening slightly, in some volcanic provinces if these things are active, right? Like the volcanic you were mentioning in that province. Do you see any movement, and what's normal?
No.
Okay.
Right now, there is no movement, nowhere in Canada. All the volcanoes are dormant and inactive, so very safe.
So if you saw movement, then that would be, get on the field.
So if we saw movement, then we had to make sure that the movement is related to magmatic activity and not something else. And if we have to saw movement, there are still some weeks, months, years, or decades before any eruption, if an eruption. It's not because you detect movement at a volcano that there will be an eruption also.
Right. So in a place like Hawaii where it's really active, and I'm sure there's lots of monitoring going on, like what would be the vertical movement? Are we talking like inches? Are we talking meters? Are we talking tens of meters?
No, we're talking about a few centimeters, maybe 5-6 centimeters. So they are doing this a lot in Hawaii and Iceland. And yeah, it's not meters. It's in the order of centimeters, yeah.
So I guess that technology wouldn't have been, like the advent of that technology wouldn't have been until recently to be able to observe that because of the precision on the satellites, I would assume, right? Yeah. So that's a recent phenomenon.
And one difficulty here is here in Canada, it's only working during the summer because if you have snow or glacier or a cloud coverage, you cannot see that. So it's another difficulty in Canada. So this system might only work during the summer or a month, especially if you go north and north. The time window is shortened to the summer months.
So I'm assuming that most people on the call are from BC. I'm sure there's some other ones that are not from BC, but in BC, within all the volcanic provinces, are you getting mostly monogenic volcanoes, or are you getting some of the other kind as well?
So where Tseax is located on the NCVP, the Northern Cordillera Volcanic Provinces, this is where you have a lot of monogenetic volcanoes. But you do have also polygenetic volcanoes. Maybe you know Mount Edziza. So this is a very wide shield volcano, so a very voluminous volcanoes with a lot eruptions in the past over there. In Wells Grey Provincial Park also, you have a lot of monogenetic volcanoes. So volcano one-off eruption, very similar to Tseax. In close to Squamish in north of Vancouver, you have Garibaldi, Mount Miguel, Mount Kelly. Those are not monogenetic volcanoes. Those are polygenetic volcanoes, massive, high-standing, voluminous volcanoes with a long-lived story.
Right. The one in Clearwater you refer to, most people might be in Kamloops that are calling in too. So we're only, let's say 2 hours away from Clearwater Lake, and between Clearwater Lake and Myrtle Lake is Coastal Cone. That's the one you're referring to, right? Yeah, right.
Yeah.
So that would be another
there are the ones that
example
are Coastal Cone and a few others that are a bit much older, but they are all monogenetic volcanoes, quite similar to Tseax in terms of volume and size and eruptive activity. Yeah.
So you're telling me if I go to Clearwater Lake on a boat trip, that thing already erupted, it's not going to erupt again? I'm good?
Well, this one in particular, there might be another one nearby, but this one, yeah.
Okay. Probably, maybe. Okay, I see.
Yeah, I can't say yes, I cannot say no, but
Yeah, says the scientist for sure. Yeah. Cool. Well, Yannick, thank you so much for your time. It was a great presentation. I got a lot out of it, and I think everyone on the call did as well. I really appreciate your time, and thank you for doing this. Much appreciated. We're going to have the next lecture series take place in person. Again, we've been rolling with Zoom calls for the last couple, but the next one's going to be at Henry Grube on February 27th, and that's Aaron Wiley. We're going to be talking about the autonomous haulage implementation at HVC at Tech. And so again, thank you, Yannick, and appreciate your time, and thank you for everyone on the call, and hope to see you in the coming weeks at Henry Grube. Thanks again.